Hello and welcome to the Spacewalkers live session in which I will present Precision Time Protocol and its functionality in the modern time-sensitive networks. As you can see on our agenda, we will describe basic functionality of PTP protocol. Then we will go into more details about different types of clocks, which are nothing else but network nodes supporting PTP protocol. We will explain the process of clock synchronization, and at the end of our session, we will present a few use cases that include omni-switches in PTP network design. Evolution in time synchronization is triggered by evolution in different technologies. Working with telecommunication networks, all of us at one point worked with NTP or Network Time Protocol, one of the first packet timing protocols. If I tell you that the first RFC related to NTP has the number 958, it would be easy to understand how far we go back in time. It was published in 1985, and the accuracy of clocks delivered by NTP was about 100 milliseconds. Of course, it evolved further on with the time up to the version 4 and was capable of accuracy in milliseconds or sub-milliseconds, which was sufficient for telecom networks at that time. But emerging technologies such as robotics, distributed printers, and smart high-voltage substations with process bus or system clusters that are divided up to several kilometers would require higher accuracy in sub-microseconds or even nanoseconds, which would be delivered through PTP protocol, a protocol that is capable of synchronizing time, frequency, and phase. So all the heterogeneous systems in the network would be synchronized with Grandmaster clock. The functionality of this protocol allows for redundancy as well as security. So let's start with basics here. PTP is a clock synchronization protocol that specifies how clocks in the network synchronize among each other. It is applicable to distributed systems with multiple nodes that communicate over the network. Synchronization is done through master-slave hierarchy. On the top of that hierarchy, there is a grandmaster clock that determines the reference time for the entire system. Slave clocks will use PTP protocol to adjust their time to the grandmaster clock in this hierarchy. Transparent clocks could be deployed on the path between master and slave clocks. They measure the time needed to transit the device, and they provide this information to downstream nodes for higher accuracy of slave synchronization. Boundary clock is the one that is used to extend the reach of grandmaster clock in the network by utilizing dual functionality. Acting as a slave on one port, it synchronizes to the grandmaster clock, while on the other port or ports, it acts as a master to downstream slave clocks. Besides mentioned nodes that support PTP protocol, and as such they are called clocks, there might also be nodes in the network that don't support PTP protocol. Management node is used for configuration of PTP clocks and monitoring them. At last but not least, within a single physical network, there might be a single or multiple PTP domains. Functionality of each clock we will describe in details further on in this session. As already mentioned, it is a grandmaster clock to which all slave and boundary clocks are synchronized to within a network. At the same time, a grandmaster clock must also be synchronized to a primary reference source or primary reference clock, which is basically a common reference clock such as Coordinated Universal Time or UTC. UTC is the primary time standard by which the world regulates time, and it is the successor of Greenwich Mean Time. Clocks that are synchronized to UTC provide the same hour, minutes, and seconds all over the world. Another example of world time standard is International Atomic Time or TAI. So how grandmaster clocks synchronize to primary reference clock such as UTC? It can be done, of course, with a Stratum 1 clock deployed on premises, but more commercial solutions depend on synchronization through global navigation satellite system such as GPS, Galileo, and some others. Those satellites might have onboard atomic clock, or they can be synchronized with ground station in order to provide PRS to the network grandmaster clocks. In order to synchronize with the PRS coming from satellite system, it is possible to deploy GPS-disciplined oscillator on premises, acting as a grandmaster clock. While long-term stability is achieved through the satellite connection, oscillator is needed for a short-term stability in case satellite connection is temporarily lost. Besides having oscillator on premises, acting as a grandmaster clock, it is also possible to install SFP with built-in GNSS support in one of the network nodes. The network node will then become a grandmaster clock for the network. Let's take a look now in more details into different PTP clocks in the network. So what exactly do we call a clock in the network? This is a network node that supports and participates in precision time protocol. You can see here a little bit simplified diagram of different blocks needed to support PTP protocol functionality. Protocol engine is the central part that sends and receives PTP messages. It takes care of synchronization either to a primary reference source or to a grandmaster clock. It does also computing of the master time by taking into account received PTP timing messages containing master time and time needed for a message to arrive. Protocol engine also holds all info about local clock, whether it is a master or slave clock, and info about grandmaster clock to which it's synchronized. It also contains information about local clock priorities and accuracy. Protocol engine contains also all information about a single or multiple PTP ports. As you can see, for every physical interface, there are two PTP logical interfaces. One is a general interface that processes general PTP messages, while event interface processes event messages or messages that contain timing information relevant to time synchronization. Timestamp generation module is timestamping all event messages on egress and egress based on the value of the local clock. Ordinary clock is a common name for all the clocks that have a single interface into PTP domain. As you could already see, ordinary clock is either a grandmaster clock or a slave clock. Grandmaster clock, to repeat it one more time, is synchronized to the UTC time as external source of time via GPS. A slave clock is a clock synchronized to a grandmaster clock. As you can see in the diagram, there is a single grandmaster clock for each slave clock to which it's synchronized. In case there are multiple nodes acting as a grandmaster clock, each slave clock will choose the best one according to defined criteria. Boundary clock, opposite to ordinary clock, has multiple physical ports into PTP domain. One port acting as a slave and synchronizing to the grandmaster clock, and one or more ports acting as a master to which other slave clocks will synchronize to. It means that all those slave clocks behind boundary clock don't sync with grandmaster clock, but boundary clock itself. For that reason, boundary clock doesn't forward messages from the grandmaster clock. Since every port on boundary clock acts as an ordinary clock port, it is also reflected to PTP blocks within a boundary clock. There is still a single local clock per node and related dataset, but all other blocks are port specific, just as in ordinary clock. Therefore, an instance of protocol engine and all other PTP blocks will be specific to each port participating into PTP protocol. So every physical port will have two logical interfaces, timestamp generation, and so on. As shown on the network diagram, boundary clock is deployed between grandmaster and slave clocks, and it is used to segment a timing network, to offload a grandmaster communication, and to eliminate the large latency generated by non-PTP devices in the network. In addition to ordinary and boundary clocks, there are also transparent clocks in the network. We recognize two types of transparent clocks, which differ in their capabilities and as such are participating in two different types of time synchronization. The first one presented here is the end-to-end transparent clock. At the center of transparent clock, there is a residence time bridge with per port assigned residence time mechanism. End-to-end transparent clock forwards all messages just like any other router or bridge, but for the event messages, and those are messages with time information, transparent clock measures a residence time within a clock and updates PTP event message with this information when it egress the clock. Updates related to this residence time are accumulated in the specific field of event message called correction field. Updates are accumulated as there could be more transparent clocks on the direct path between master and slave clock. So once this message arrives to a slave clock, it will contain accumulated residence time of all transparent clocks on the path. As you can see on the diagram, residence time will be measured between any two ports, as it is possible that residence time for a message are different between different ports. Time steps are, of course, based on the local clock of the transparent bridge, and not on the grandmaster clock. Therefore, optionally, for more accurate measuring of local residence time, it would be beneficial for a local clock to be synchronized with the grandmaster clock for more accurate synchronization. In this example, you can see event message ingressing port 1 and egressing through port N. This message will be timestamped on ingress and egress, and residence time bridge will calculate a residence time as a timestamp on egress port minus timestamp on ingress port. This value will then be accumulated into correction field of event message. Besides end-to-end transparent clocks, there are also peer-to-peer transparent clocks that have additional capabilities compared to any-to-any transparent clocks. This capability is to measure also link delay in addition to residence time. Link delay is calculated based on specific PTP messages exchanged between link peers and will be accumulated to the correction field together with residence time measured by residence time bridge. At the end, correction field will have correct time needed for the message to pass through all the peer-to-peer transparent bridges on the path between master and slave. The benefit of peer-to-peer transparent clock is that slave clock is immediately informed about timing value of the actual path through the network. In the case of end-to-end transparent clock mentioned earlier, additional steps are required to measure link delay between master and slave, which takes also additional time. It is important to mention here that peer-to-peer and end-to-end transparent clocks don't interwork. Due to different capabilities, each transparent clock participates in different synchronization methods. It is boundary clock that can bridge these two different regions using different methods on different ports of the boundary clock. Within PTP network, there is also a management node, and it is used for configuration and monitoring of deployed clocks. Using management messages, a management node will receive all attributes of local clocks and ports. Now let's take a look at the process of synchronization. Synchronization process refers to synchronizing of ordinary and boundary clocks within a network. The process of synchronizing a grandmaster clock to a primary reference source is not a part of the standard. Synchronization is performed in two steps. The first step is to choose the best master that will be used as a source of time using best master clock algorithm. The second step is to synchronize with that master either through delay request response or through peer delay mechanism. Based on the chosen synchronization process, end-to-end or peer-to-peer transparent clocks will be used respectively. The best master clock algorithm compares data describing two clocks in order to determine which data describes the better clock. When PTP port receives announced message, the message sent by foreign master describing its own clock attributes, first it compares received attributes with its local attributes to decide which clock is better. The same algorithm also compares attributes between two or more announced messages received from two or more foreign masters. This process is perpetual in the PTP network. As a result of that algorithm, a master-slave hierarchy will be created throughout the network, where each local PTP port will decide upon port state that could be master, slave, or passive. Some values of data set describing the clocks and used by algorithm are user configurable, such as 2 levels of priority. Other values, such as clock stability and accuracy, are clock origined. As you can see on the diagram, more complex topologies could have physical loops through which data forwarding is not blocked by layer 2 or layer 3 loop prevention protocols. In that case, a clock could receive announced messages from the same foreign clock by 2 ports, and it is on PTP protocol to choose one that will become a slave port used for synchronization with the master, while the other ports will change to a passive state, meaning port is neither the master on that path nor will synchronize to a master. Once master-slave hierarchy is established, a synchronization can begin. By synchronization, we want to reduce the clock offset as much as possible, and ideally, there will be no offset at all between different clocks in the network. Clock offset is a time error between a master and a slave time measured at the same instant. Presented here are details of delay request response synchronization. A master clock will send sync message to a slave with T1 timestamped time information at egress. This T1 time is a precise time of the master clock plus residence time in the master clock needed for the message to leave the clock. This residence time will be recorded in the correction field of the sync message. Optionally, precise time of the master clock can be sent within follow-up messages. Upon ingressing a slave clock, sync message will receive timestamp T2. As time error or clock offset is calculated as the difference between time on 2 clocks minus path delay, we still have to calculate a path delay between a master and a slave. A path delay of the path from a master to a slave can be calculated as T2 minus T1, both times already known to a slave clock. Since path delay in the opposite direction might be different, for the calculation of time offset, a mean propagation time will be used between propagation times in both directions. Propagation delay calculation from a slave to a master is initiated by a slave clock sending delay request message at time T3. With this message, slave clock requires master clock to send back time information about receiving this request message. This information is sent from master clock to a slave clock using delay response message. At this point, a slave clock has all information needed to calculate the clock offset between a master and a slave. This is the view of the same delay request response mechanism, but with 2 transparent clocks on the path between master and slave. Both transparent clocks have to be of end-to-end types. As previously mentioned, end-to-end transparent clocks have ability to calculate residence times of messages within the clock, which is calculated as egress timestamp minus ingress timestamp. The value is then accumulated to the correction field of sync message. The principle of calculation the clock offset is the same as on the previous slide, but in this case of using transparent end-to-end clocks, the difference is that correction field will include residence time of transparent clocks, while mean path delay will be calculated using path delay between multiple clocks. Peer delay mechanism measures link propagation delay between 2 PTP ports. Link delay should be measured by both ports regardless if they are actively used for time synchronization, or any of ports might be in a passive state, or a link is not forwarding due to layer 2 or layer 3 loop prevention protocols. While ordinary and boundary clocks support peer delay mechanism regardless if port has a master or slave status, only peer-to-peer transparent clocks could be used, as only this type has ability to store link delay information in addition to residence time delay information. Both values will be accumulated into correction field message. Link propagation delay calculation starts by any of clocks initiating peer delay request message, which is timestamped at T1 as its egress the port. This message is received by link peer clock at time T2. Link peer clock initiates peer delay response message at T3, and the value of time between initiating response message and receiving request message, so T3 minus T2, will be recorded within the message. Once peer delay response will be received and time-stepped on ingress with T4 time, clock 1 will have all info in order to calculate mean path delay on the path. The same process will be repeated by clock 2, by which clock 2 will also have information about link delay. As you can see, with peer delay synchronization using peer-to-peer transparent clocks, slave clock can immediately calculate the offset from the master clock, as info about residence times and path propagation delay times are included in the correction field of the sync message. The accuracy of any PTP system is limited due to different factors, and here are some of them. Propagation asymmetry caused by not having the identical path and consequently path delay in both directions between master and slave. This asymmetry will be noticed especially if some non-PTP capable nodes are placed on the path. To minimize the error, clock offset is calculated with mean path delay values and correction values. In case of timestamping performed at application level by software, a protocol stack will create delay fluctuation. Therefore, it is mandatory to perform timestamping at Ethernet PHY layer for more precise synchronization. In order to avoid any fluctuation due to network congestion and egress buffering and queuing, it is recommended to assign the highest traffic class to PTP protocol messages. Of course, the accuracy of clock itself generating timestamps is one of the factors as well. Let's take a look at some different PTP profiles available today. Within PTP protocol, there are multiple options and features available. Some of these options are more important for some industries than for the others. Preferred default values of some of the options might be differently prioritized among industries, and some industries even require new profile-specific TLV fields to be created. The standard defines two profiles for synchronization that we have already discussed in this session. Those are peer delay and delay request response profiles. Both synchronization profiles are using best master clock algorithm for choosing the master clock. On the slides we have two power profiles defined by related standards. IEC IEEE 61850-9-3 defines a power utility automation profile for use in substation applications. This profile, among other parameters, defines peer-to-peer delay measurement profile. It defines also accuracy of different clocks in the network, and it defines maximum of time error budget of 1 microsecond, meaning there should be no more of 15 transparent clocks and 3 boundary clocks in line. Further extension of this standard is covered in C37.238 standard, defining profiles for phasor measurement units, used to measure electrical quantities in power grids. There are also PTP profiles related to telecom industry. Here you can see three major telecom PTP profiles defined by International Telecommunication Union. The first one is G8265, a profile for frequency synchronization used mainly for synchronization of cellular stations. The second one is G8275.1, a profile for time and frequency synchronization with full timing support from the network, and there is a G8275.2, also profile for phase and time synchronization with partial timing support. Detailed parameters and options related to each of these profiles could be found in the standard. Let's take a look at PTP support provided by OmniSwitches and NOKIA IP/MPLS gear and possible designs that we can create combining both products. Different OmniSwitch nodes support transparent clocks, while end-to-end transparent clocks are supported on 6465, 6560, 6860, 6865, and 6900 models X72 and Q32. Peer-to-peer transparent clock is supported only on 6560 switches. Besides supporting built-in Stratum 3 and upgraded Stratum 3E standard clocks, Nokia has also a wide range of nodes supporting PTP protocol. On selected product lines and models, Nokia supports all types of clocks, including master, slave, boundary, and transparent clocks. Selected Nokia products also support telecom and power PTP profiles as previously described. Here is an overview of specific product lines supporting PTP protocol, but please check datasheet for a specific model support. In this example of LTE network, the following design of precision time protocol is applied. To synchronize the network time with the primary source reference, two GPS disciplined oscillator nodes are installed for redundancy purposes. They are both synchronized with the Universal Coordinated Time via GNSS system. They act as the grandmaster clocks to the network nodes. The backhaul network is based on IP/MPLS core, therefore Nokia products will be used on which boundary clocks will be configured. Slave port of boundary clocks will be synchronized to grandmaster clock, while master port will be used for synchronization of slave clocks on LTE base stations. Hardened product lines of Omni switches will be used in the access network layer, to which base stations will be connected. Omni switch will provide transparent end-to-end clock for better accuracy of base station slave clock synchronization. In this classical three-tier design, IP/MPLS technology is deployed at the core and distribution network. Therefore, it is built upon Nokia IP/MPLS product lines, such as 7250 AXR or 7210 SAS. At the access network layer, Omni switches are deployed at the stations, and since there is a need for hardened and non-hardened layer 2 nodes, OmniSwitch 6465 and OmniSwitch 6560 will be installed. End-to-end transparent clock will be enabled on OmniSwitch products that are placed on the path between boundary and slave clocks as configured on Nokia equipment.
I hope you enjoyed this session. Let's now close with some key takeaways. Time synchronization is crucial for service providers building LTE and 5G networks, as well as for some industries such as utilities. Precision time protocol defines multiple types of clocks within a network, and although not all clocks are supported by Omni switches, its PTP support increases precision of time synchronization of other nodes in the network. Keep enjoying your Spacewalkers live event. I'm looking forward to interacting with you on this and other topics on the Spacewalkers platform. Take care and see you soon.